So in this video, the topic for discussion is numerical solution of algebraic and transcendental equations. In this video, we shall discuss three methods: bisection, Regula, Falsi, and Newton-Raphson. So these three methods will be discussed in this video, and these methods are used to find one real root of algebraic or transcendental equation. Whenever you are given an equation, to find a root of this equation, we use one of these methods. And these methods will give one root at a time. So let's discuss what is bisection method. In bisection method, to find a real root of the equation fx equal to 0, where fx equal to 0 may be algebraic or transcendental. So this equation may be algebraic or transcendental. To find the real root of this equation, first of all, we need to locate the root. So I have already told you how to locate the root. So location of the root is by intermediate value theorem. So suppose a0 and b0 be two real numbers such that f of a0 into f of b0 less than 0. So this condition will ensure that there exists at least one root in the interval a0 b0. So whenever you find an interval containing the root, then in bisection method, the idea is to bisect the interval. This is the actual root. In this graph you see alpha is the actual root. So how to reach near the root when you find the root is in the interval a0 b0? So the idea is bisect the interval by taking a0 plus b0 by 2 as x1. So this point x1 is in the middle of a0 and b0 and it is near the root. Then we find that we have two intervals. This is bisected into two intervals, a0 x1 and x1 b0. Again, the root will lie in one of these two intervals. Again, we check the conditions: f of a0 into f of x1 less than 0 or f of x1 into f of b0 less than 1. So depending on these two conditions, we take new interval as a1 b1, where a1 b1 is a0 x1 if this condition is satisfied, and a1 b1 is x1 b0 if this condition is satisfied. So in this graph we have this interval a0 x1 as a1 b1 because the root lies in this interval a0 x1. Again we bisect the interval and take x2 as a0 plus x1 by 2. So this is x2. So we are more close to the root, and this process will go on until we get the root. So this is how we find a real root in the interval a0 b0 by bisection method. So in this method we keep on bisecting the intervals in which the root lies. So this is the idea of this method. So let's write it mathematically. So let x1 equal to a0 b0 by 2, where a0 b0 is the interval containing the root, and the new interval I1 will be a1 b1 depending on one of these two conditions in which the root lies. So I1 will be a1 b1 depending on whether the root lies in a0 x1 or x1 b0. Then this I1 is contained in I0 because I0 is bigger interval, I0 is a0 b0 and I1 is a0 x1. So length of this interval I0 is b0 minus a0, length of this interval a0 b0. So when you want to find the length of this interval, you get b0 minus a0 is the length. And what is the length of I1? Length of I1 is b1 minus a1, which is b0 minus a0 by 2 because it is half in the length. Then again we take x2 as a1 plus b1 by 2. Again we bisect the interval in which the root lies, and the new interval I2 will be a2 b2 depending on whether the root lies in a1 x2 or x2 p1, whether the root lies in one of these intervals. Again the length of this new interval I2 is b0 a0 by 2 square, that means b0 minus a0 by 4. So this is 1 by 4 in the length. Continuing in this way, we get at kth step as xk plus 1 equal to ak plus bk by 2, and the new interval as ak plus 1 bk plus 1, where this ik plus 1 is the smallest interval, ik plus 1 is contained in ik, and so on up to I0. And length of this ik plus 1 is b0 minus a0 upon 2 to the power k plus 1. So this is the length of this interval ik plus 1. So these x1, x2 up to xk plus 1, these approximations will tend to the real root in successive steps, and after some times, a number of steps, we get the real root. These repetitions are called iteration process. Iteration means when we use the result obtained at one step into another step. So this is an iterative process, and this process will stop when the desired condition for desired accuracy is satisfied. The desired accuracy may be a root up to 2 places of decimal, 3 places of decimal. So depending on the desired accuracy, the process will stop. Now take an example. Find a real root correct to the 3 places of decimal of the function fx equal to log x square plus 1 plus cos x plus x. So you are given this function and you have to find one real root of this function. So one thing you should note that whenever you are going to use the calculator for calculating the root or finding the root of this equation, always convert the mod of your calculator in radian. Mod should be in radian because by default mod of calculator is in degrees. So convert the mod into radian because this function has trigonometric function and real function also. So here x is in not in degrees, x is in radians. So numbers on real number line are in radians. That's why we have to use the mod of the calculator as radian. So after converting the mod into radian, you find the interval in which the root lies. So the root lies in the interval -2 to -1 because f of -2 is negative and f of -1 is positive. So take a0 as -2 and b0 as -1. The next approximation to the root is obtained by the bisection method as xk plus 1 equal to ak plus bk by 2. This is the formula for bisecting the interval. Now we calculate the next approximations in the table. So in this table, these are the columns. So for k equal to 0, this will be a0, a0 is -2. This is b0 which is -1. F of a0, a0 means f of -2 which is -0.8067. F of -1 which is 0.2334. And what is this xk plus 1? This xk plus 1 is ak plus bk by 2. So take sum of these two and divide it by 2. So xk plus 1 is ak plus bk by 2. That means x1 will be, for k equal to 0, this is x1. So a0 plus b0 by 2. So that is equal to -1.5. And value of the function at -1.5 you calculate and write here. So these are the values. This is at f of x1, which is f of -1.5. Now in the next step, how to find the new interval in which the root lies? So look at these three values, this one and this one, and find which two are of opposite signs. So we find that f of bk and f of xk plus 1 are of opposite signs. So f of bk is corresponding to -1 and f of xk plus 1 is corresponding to xk plus 1. So the new root lies in the interval -1.5 to -1. So this is the new interval. So -1.5 is this and -1. So k equal to 1. For k equal to 1, we have the new interval in which the root lies, -1.5 to -1. And repeat the same procedure. Write down the values of f of ak, that means f of -1.5, f of bk, that means f of -1 here, and x2. Now x2 will be average of these two, -1.5 -1 by 2. So that will be here, and then value of the function at x2. So these are the entries. So new interval is this in which the root lies, values of the function at these points, then x2. This x2 is obtained by a1 plus b1 by 2. These are a1 and b1, new interval. So -1.25 is the new value, and this is the value at -1.25. Again, you find the interval in which the root lies. So look at these three values. So at every step you have to check the three values of the function, whether they are of opposite signs, which two are of opposite signs. So we find that this time f of ak and f of xk plus 1 are of opposite signs, and we find that f of ak, this -2 minus 0.2506 is corresponding to minus 1.5 and 0.0063 is corresponding to minus 1.25. So this time the root lies in the interval minus 1.5 to minus 1.25, because at minus 1.25 we have negative value of the function, and minus 1.25 we have positive value. So new interval now is this, which is a2 b2, and we repeat the same procedure until we get the real root. So we have to repeat this process a number of times. And where to stop? To stop, we look at the given required accuracy. The accuracy is up to 3 places of decimal. Therefore, we look at these values. So look at this column only. In this column, we find that the values of xk plus 1 are minus 1.2578, then minus 1.2539, and so on. So we have to repeat the procedure until we get 3 places of decimal repeating. So here we see that minus 1.2569 and minus 1.2564. So 3 places of decimals are repeating in this step 9th and 10th. Then we can stop here and we can write the root. So if we look at the values of xk plus 1, we find that the 3 places of decimals become constant in 9th and 10th steps. Therefore, we can take approximate root as minus 1.256 up to 3 places of decimal. So if you find x11 minus x10, because this is x11 and this is x10, if we find the difference, we find that this is equal to 0.0005, which is less than 10 to the power minus 3. That means the desired accuracy. Therefore, the approximate root is x equal to minus 1.256. So this is how this method works. But you see that the number of steps here 10. That means we have to repeat this procedure up to 10 steps to get the real root up to desired accuracy. That's why this method is very slow in nature. This method is very effective, but it is slow. Now look at another example. Here specifically you have to find the negative root of the equation x cube minus 2x plus 5 equal to 0. Correct to 3 places of decimal using bisection method. So here you have to find the negative root. So you have to search the root in the negative direction, that is minus infinity to 0. So again you find the interval in which the root lies. So by hit and trial I have found that the interval is minus 3 to minus 2, because f of minus 2 into f of minus 3 less than 0. So a negative root lies in the interval minus 3 to minus 2. So again taking a0 as minus 3 and b0 as minus 2, the next approximation is given by the bisection method as xk plus 1 equal to ak plus bk by 2. And all those calculations for the next approximations are in this table. So for k equal to 0, again you have a0 is minus 3, b0 is minus 2, f of a0 is minus 16, f of b0 is 1, and this xk plus 1, that means x1 is minus 3 minus 2 by 2. So this is minus 2.5 and so on. So if you repeat this process, again you find that you have to go up to 9th or 10th steps to get the root, because here we see that at 9th and 10th steps we get 3 places of decimals constants, minus 2.094 and minus 2.094 up to 3 places of decimal, they are same. Therefore, we can take the approximate root as x equal to minus 2.094. So we have seen in these two examples that method is very slow. It requires a number of steps to find the real root. Therefore, this method is effective but not efficient. Its efficiency is very low. Therefore, we need some other methods which must be faster than this bisection method. So the next method we are going to discuss is the Regula Falsi method. This method is faster than the bisection method. So again here, to find a real root of fx equal to 0, whether algebraic or transcendental, again we find the interval in which the root lies. So here the root lies in the interval a0 b0. So this is the idea of this method. So in this method, what we do, once we find the interval a0 b0, we find the chord joining these 2 points, a0 f of a0 and b0 f of b0. So we find the equation of this chord joining these 2 points, and the point where it cuts the x-axis is taken as the new approximation. So here x1 is the point at which this chord cuts the x-axis. So this is the new approximation. Again, we check whether root lies in a0 x1 or x1 b0. So depending on these two conditions, we select the interval. So here in this graph, the root lies in a0 x1. So we select this interval. Again, we find the chord joining a0 f of a0 and x1 f of x1, and we take new approximation as the point of intersection of this chord with the x-axis. So in this way, we repeat this procedure until we pass through this root. So ultimately this chord will pass through this root. So when it passes through the root, that point is taken as the root of the equation. That point of intersection is taken as the approximate root of the equation. So this is the idea. So here we approximate the real root by taking chord of the curve. So let's see how this procedure works. So chord joining 2 points a0 f of a0 and b0 f of b0 is given by this formula. This is the equation of the chord joining these 2 points. Now suppose this chord cuts the x-axis at x1, then by taking y equal to 0 and x equal to x1, so put y equal to 0 and x equal to x1 in this equation and solve this. For x1, you find this is x1 and the new interval is a1 b1, depending on whether the root lies in a0 x1 or x1 b0. So select the interval in which the root lies and again find the chord joining these 2 points a1 b1, a1 f of a1 and b1 f of b1. And again suppose this line, this chord cuts the x-axis at x equal to x2. So put x equal to x2 and y equal to 0 and solve it for x2. You get x2 as a1 f of b1 minus b1 f of a1 divided by f of b1 minus f of a1. So you can see the trend of x1, x2. So you can generalize this formula. So you can generalize these formulae and continuing this way, we get at kth step xk plus 1 equal to ak f of bk minus bk f of ak divided by f of bk minus f of a. So this is the formula for the next approximation and the interval will be this ik plus 1. Again x1, x2, x3 up to xk plus 1 are the successive approximations. So therefore this iteration process can be stopped when we get the desired accuracy, and desired accuracy will be obtained when two successive approximations xk plus 1 and xk, their difference will be less than 10 to the power minus n. 10 to the power minus n will be the desired accuracy, whether you want to find the root up to 3 places of decimal or 2 places of decimal or 4 places of decimal. So depending on this will be the accuracy. So this is the regular Falsi method. So let's take the same example and see how many steps are required to find the root. So we have already obtained the interval in which the root lies. So interval is minus 2 to minus 1. So I'll take a0 as minus 2 and b0 as minus 1. The next approximation is given by the regular Falsi method. In bisection method, we have xk plus 1 as ak plus bk by 2. But here we have xk plus 1 as this formula. So again, we prepare the table as usual, k, ak, bk, f of ak, f of bk, xk plus 1 and f of xk plus 1. The procedure is same. For k equal to 0, what is a0? a0 is minus 2, b0 is minus 1. F of a0 is minus 0.8067. F of minus 1 is 0.2334. Xk plus 1 is by using this formula. So how to use this formula? Using these values. So how to find x1? X1 is a0 means minus 2 into f of b0 is 0.2334 minus b0 is minus 1 into f of a0 minus 0.8067 divided by f of b0 2334 minus 0.8067. So when you solve this, you get x1. Okay, so it's very simple. In a particular steps, you have to use these 4 values in this formula to get xk plus 1. So in this, we get xk plus 1 is minus 1.2244 and f of xk plus 1 is 0.0310. This is f of x1. Okay, this is f of minus 1.2244. So again we check the interval in which the root lies. So interval is these three values. We check these three values to find the interval in which the root lies. So we find that f of ak and f of xk plus 1 are of opposite signs. So the new interval will be minus 2 and minus 1.2244. So repeat the same procedure. You get x2 as minus 1.2532. So using these four values in this formula, you get x2 as minus 1.2532, and this is at minus 1.2532. So repeating this procedure a number of times, we find that xk plus 1 is constant up to 3 places of decimal in the second and third steps. So in second and third steps, we find that xk plus 1 is constant up to 3 places of decimal. So here x4 minus x3, if we find the difference, we find that this is less than 10 to the power minus 3. So approximate root is minus 1.256 up to 3 places of decimal. So here we find that the number of steps taken is very small. Here we get the root in 3 steps. Okay, so which is almost less than 50% of the steps in bisection methods. Therefore this method is faster than the bisection method. That's why we prefer this method over bisection method. So here we get root in almost 3 or 4 steps, and in the bisection method we required 9th or 10th steps to get the value minus 1.256. To find the real root of this equation, again we find the interval in which the root lies. So first of all you find the interval AB in which the root lies. Okay, then in this interval you take an arbitrary approximation to the actual root. So take x0 in this interval as the initial approximation. This x0 is called the initial approximation or the starting point of this method. So you have to select this x0 in this interval suitably so that you can get the root. Now what is the idea of this method? So in this method, look at this graph. So in this method, we find the tangent at this initial approximation. So initial point is x0 f of x0, this point. So at this point we find the tangent to the given curve. So what is the equation of the tangent? Equation of the tangent is y minus y0 f dash x0 x minus x0. This is the tangent to the curve at this point, initial point. Okay, and the point where it cuts the x-axis, is taken as the new approximation. So at x equal to x1, suppose y equal to 0, it cuts the x-axis at x equal to x1. So what is the value of x1? Put x equal to x1 and y equal to 0. So you get x1 as x0 minus f of x0 divided by f dash x0. So this is the point x1 where it cuts the x-axis. This is taken as the new approximation. Okay, and similarly starting from x1 f of x1, we find tangent at this point x1 f of x1, and we take the new approximation x2 where it cuts the x-axis. So by repeating the same argument, we get x2 as x1 minus f of x1 divided by f dash x. So repeating this procedure up to k times, we get xk plus 1 equal to xk minus f of xk divided by f dash xk. So x1 x2 up to xn or xk plus 1, if you find in this way, you get the real root alpha. You reach near the real root. So x1 x2 x3 up to xk plus 1 will tend to the real root alpha in successive steps. So again stopping criteria is same. Whenever you find xk plus 1 minus xk less than 10 to the power minus n, which is desired accuracy up to 3 places of decimal or 2 places of decimal, you can stop this method. So this is the idea of Newton-Raphson method. So here we approximate the root by taking tangent to the curve. In regular Falsi method, we approximate the root by taking chord of the curve. Okay, so here we approximate the root by tangent. So this is the procedure. The tangent at point x0 f of x0 is given by this equation I have already explained. So this is how you get the formula for Newton-Raphson method. So this is the formula for Newton-Raphson method. Now this method is very fast as compared to bisection and regular falsi. So this is the formula which you have to use. So consider the same example which we have used in bisection and regular falsi methods. So again, find the interval which we have already found, -2 to -1. In this interval root lies. Now you have to use Newton-Raphson method. So how to choose this initial approximation? This method is very sensitive to initial approximation x0. So one simple way to choose this x0 starting point between this -2 and -1. How to choose this x0? So look at x0 or take x0 near to the actual root. Take x0 near to -1. So x0 near to -1, you can take any value near to -1, either -1.25 or -1.30 or -1.35, whatever it is. So you have to take any one value of this x0 near to -1. Okay, this is a rough method, not necessary that you take near to -1. You can take -1.5 also. You can choose any value between -2 and -1. Using this criteria, roughly, we select x0 as -1.3. We assume that root is close to -1, so we take x0 as -1.3. You can take x as -1.25 also. So starting from x0 equal to -1.3, the next approximation is by Newton-Raphson method. So in Newton-Raphson method, we require f of xk, which is given, and derivative of this function. So derivative of this function is, if you find derivative of this function, this is 1 upon xk square plus 1 to xk minus derivative of cos minus sin k and derivative of the xk 1. So we require both f of xk and f dash xk. So again, starting from this x0 -1.3, these are the columns. So you have to prepare this table here. So for k equal to 0, we have x0 is -1.3 starting point. And what is f of -1.3? So f of -1.3 is from here, and f dash -1.3 is from here. Find both the values. This is f of 1.3 -1.3. So put -1.3 here. You will get this value. And f dash -1.3. Put -1.3 in this f dash xk. You get 0.9970. Okay. Then how to find xk plus 1? Xk plus 1 is very simple. Xk minus f of xk divided by f dash xk. So -1.3 minus -0.0430 divided by 0.9970. This is xk plus 1. So to find xk plus 1, you have to use these three values in this formula. So here we get -1.2569 and value of the function is -0.0004. So here you see in the first step itself we get the value -1.256, which we were getting in 4 or 5 steps in regular falsi and 9 and 10 steps in bisection method. So this value -1.256 was obtained in bisection method in 9 and 10th steps, in regular falsi in 4th or 5th steps, and in Newton-Raphson in 1 step only. Again, taking the new value, whatever it is, x1, starting from x1, f of x1, f dash at x1, and you get this value -1.256 again. So up to 3 places of decimal, this value is repeating up to 3 places of decimal. So the approximate root is -1.256. If you repeat this method again, you get the same value, -1.2565, and value of the function is 0 up to 4 places of decimal. So the approximate root is -1.256 up to 3 places of decimal. So if you round off it properly, this is -1.256. So you can see here is 1 or 2 steps are required to find the real root. Next example, the negative real root of this equation. So interval -3 to -2. Again, we compare these two values. F of -2 is 1 and f of -3 is 16, -16. So you can see it is very clear that root is near to -2 because f of -3 is -16. Suitable value is -2.25 or 2.20. Using the Newton-Raphson method, f of xk and f dash xk, you can find and you can form a simple formula. Instead of finding f of xk and f dash xk, we find a formula for xk plus 1. So starting from minus 2.25, these are the entries. So sometimes you can avoid these two columns directly. You can use this. Xk is minus 2.25, put minus 2.25 directly here. So you can get xk plus 1. So you can avoid these two columns sometimes. So you can form a simple formula in Newton-Raphson method. So here we see that minus 2.1066 is the first approximation. This is x1, and starting from x1 you get 2.0946 in the second step, and in the third step also you get this value. I think this is 9. So minus 2.0946 and minus 2.0946 first and second steps. So approximate root is minus 2.0946. So approximate root is this, if you round off it up to 3 places of decimal. The method is very fast. So this is about solution of numerical methods for transcendental algebraic equations.